So my name is Luís Machado. I think I'm the only Portuguese guy that is around.
Welcome. Welcome.
Thank you. So my talk will be about rolling homogeneous symmetric spaces, and this is a joint work with a Polish guy, Krzysztof Krakowski, and my ex-supervisor, Fátima Leite from the University of Queen. So this one. Okay. So there are two main goals in this work. First, we want to present a unifying theory that describes the rolling motions of the homogeneous symmetric spaces that have been appeared in the literature. And secondly, we would like to establish the connection between the kinematic equations of the rolling motions with the Lie algebra decomposition associated to these symmetric spaces. So the outline of the talk is this one. So first I will recall the definition of rolling. This is a technique that, as far as I could understand, nobody here talked about this before. Then I will present the main notions about homogeneous symmetric spaces in order to present the main results about rolling of remaining symmetric and homogeneous spaces. In this case, we will show how the Lie algebra structure of the composition associated to the symmetric space is related or is connected to the kinematic equations of these rolling motions. I will show this, well, it's not show, but I will try to illustrate these theoretical results with few examples. I would like to notice that we tested all the examples that are known, but in this talk I will restrict to the Euclidean sphere, which is the typical one, then the Lorentzian sphere, which is a pseudo-Riemannian manifold, and finally the Grassman manifold, which is a manifold that is embedded in the vector space of symmetric matrices, but contrary to the previous two examples, it has no codimension equal to 1. Finally, I would like to finish the talk with a conjecture, because since all the examples that are known corroborate the theoretical results, but up to now we could not have been able to establish a complete proof for this conjecture. So, in order to define what a rolling map is, I will start with a Riemannian manifold of dimension m that we call the ambient manifold. This is where everything happens. We can think that M tilde, for simplicity, is the Euclidean space Rm. And then I denote by G tilde the group of isometries that preserve orientation. This is something that is required for this kind of motions, the orientation of the preserving of orientation. So if M tilde is the Euclidean space Rm, then the group of isometries is the semi-direct product between the special orthogonal group and the Euclidean space Rm. And finally, we will consider two n-dimensional manifolds, so two manifolds with the same dimension, isometrically embedded in the ambient manifold. Okay, so we say that a map between a closed interval of the real numbers to the group of isometries is a rolling map of M, of the manifold M, upon the manifold M0 with the rolling curve sigma, which is a smooth curve in the manifold M. If for all t, these conditions are satisfied. So we have the rolling conditions and these two non-holonomic conditions, the no slip and the no twist condition. So the rolling condition simply means that if we apply this rolling curve, this rolling map to the rolling curve sigma, we obtain a curve in the manifold M0 that we call the development curve of this rolling curve sigma. And this second condition simply means that at the contact point, both manifolds have the same tangent space. So the no-slip condition means that the velocity vector at the contact point is the same for the two curves. And we have these two complementarity conditions that describe the no-twist conditions of rolling. That means that when we differentiate this operator key dot key minus 1, where key is the rolling map, then this differential operator maps tangent vectors into normal vectors and the other way around. So it maps normal vectors into tangent vectors. So, so here is a picture illustrating the rolling motion. So this is the manifold that is roll upon this manifold M0. Okay, the sigma, the green curve is the rolling curve in the manifold M, and when the manifold is rolling, so we get the development curve here in the manifold M0. Okay, so there is an important property that I would like to mention about this structure of this differential of the operator key dot key minus 1 that says basically that, well, it describes basically the no-twist conditions, the two no-twist conditions, that says that for an appropriate choice of coordinates in a neighborhood of the contact point, then the structure of this differential mapping is given in matrix form as this block matrix structure that you can see here. Okay, so what we will see here in this talk, or, well, I'm not going to enter into details, but the idea is that what we did was to show that if the manifold M that is rolling is a symmetric space, then the structure of this differential operators is captured from the decomposition of the Lie algebra associated to this symmetric space. So basically, that's what we did in this work. So so about homogeneous and symmetric spaces, we start with the transitive action of a Lie group G on a manifold M. So if we pick an arbitrary point M0 in the manifold M and consider the subgroup of the Lie group G that preserves or that fixes the point P0, then we get a group, a subgroup of G that is called the isotropic or the stabilizer group at the point P0. So in this case, the set of left cosets of H is a homogeneous space that is proved to be isomorphic to the manifold M. So we say that this homogeneous space is reductive if it is possible to obtain a subspace or a vector space P of the Lie algebra G of this Lie group G, such that that Lie algebra can be decomposed into the direct sum of the Lie algebra of the isotropic group and this vector P, where P is invariant with respect to adjoint representation of H. If additionally this vector space P brackets into H, then we say that the homogeneous space is also a symmetric space. So this is the basic idea. So in our work, we had to assume all of these conditions, that the homogeneous space is reductive and symmetric. So in this case, so the natural projection of the Lie group G into the manifold M is a Riemannian submersion, meaning that we can identify the tangent space of M at the point P0 with the vector space P. Okay, so there are two important properties of the rolling maps that can reduce the study of the rolling a manifold into a general manifold to the study of rolling a manifold upon an affine tangent space to a given point. So these are the symmetry property. That simply means that if we are rolling a manifold upon another manifold, with rolling curve this green one, and with development curve this red one, then the inverse of that map simply do the opposite. So what it is doing is to roll this affine tangent space upon the manifold, but now the rolling curve is the red one and the development curve is the green one. So after that, if we roll now the affine tangent space over the last manifold, so the final manifold, along this development curve in red, we get the orange curve that is the development of this red curve into the final manifold. So if we compose these two mappings, we get the roll, let's say, we can study or describe the rolling motion of this initial manifold into the last manifold, where this orange curve is nothing but the development of the green curve on the final manifold. So the idea is that basically it's only required to study the rolling of a manifold upon its affine tangent space to a given point. Okay, so in the talk I will assume that the ambient manifold, the space where everything happens, is the Euclidean space Rm, but there were several results that we could prove in a more general context when the ambient space it's not necessarily required to be the Euclidean space. So I start with a remaining symmetric and homogeneous space isometrically embedded in this ambient manifold. Okay, as I just said, the group of isometries that preserve orientation in the ambient space Rm is this semi-direct product, and therefore a rolling motion will be a pair where this R will be a curve in the special orthogonal Lie group and as a curve in the Euclidean space Rm, and we assume that this map is describing the rolling motion of the symmetric space M upon an affine tangent space to the given point P0 or to a given point P0. So the Lie group action enable us to establish the action of this mapping on M and on T Pm by just doing this. Okay. Are the natural, let's say, mappings. Okay, so what we were able to prove was that if we have this decomposition of the Lie algebra of the group G into the direct sum of the Lie algebra of the isotropic group and the vector space P, then we prove that H maps tangent vectors to tangent vectors and normal vectors to normal vectors, while the vector space P, okay, sends points from the tangent space to the normal space and the other way around. Okay, so the idea is that we could prove this in a more general context, but these last two conditions we could not prove if M tilde is not the Euclidean space. So in this case, we prove that the differential of this operator is in fact an element of P. Okay, it has only components here and not here. Okay, so some examples. So I will start with the sphere, which is a typical homogeneous symmetric space under the natural action of the Lie group SON plus 1. We fix the point P0, let's say the south pole in this case, and the isotropic group is can be well, it's a set of the matrices or block matrices that can be partitioned like this, and is isomorphic to SON, and therefore the Lie algebra decomposition associated to this symmetric space is this, where H is the isomorphic to the Lie algebra of symmetric matrices n by n, and P is this subspace of matrices that are also skew-symmetric but has block diagonals equals to 0. Okay, so in this case, so it is well known in the literature that the kinematic equations for the rolling sphere, that I'm not going to derive them here, but they are very well known. You can check in the paper of Judgvik from '97. And in this case, so the kinematic equations are given by this system of first-order differential equations. They are derived from the no-slip and the no-twist conditions. So the no-slip gives one of the differential equations and the no-twist gives the other one. So in this case, the derivative of this operator is this r dot r minus 1. And from here, this is equal to minus A, which is this matrix, and is an element of P, because P was this one. So A has the same structure as the elements of P. So, okay, for the case of the Lorentzian sphere, which is a pseudo-Riemannian manifold, because we start with the pseudo-orthogonal Lie group SON1, where it is, let's say that it's a modification of our typical SON, but here we are using the signature matrix, which is a diagonal matrix that has all the entries equals to 1, except the last one, which is equal to minus 1. So in this case, this Lorentzian sphere is also a homogeneous symmetric space under the natural action of this pseudo-orthogonal Lie group given by this. And the isotropy group at a given point, that in this case we fix the north pole, just to be different. In this case, the isotropy group is isomorphic to SON minus 1, 1. And this is the composition of the Lie algebra associated to the homogeneous symmetric space, where H is the Lie algebra of the isotropy group, and P is that vector space. Okay, so in this case, so the kinematic equations for the rolling motion are given by also this system of differential equations, where this U of t is an element lying in the tangent space of the Lorentzian sphere at the point P0. So in this case, the derivative of that operator is also given by r dot r minus 1, and from here it is equal to this expression, which is obviously an element of P, because this is a skew-symmetric matrix, and that has the form of these elements here. Okay, so the Grassman manifold, contrary to the other two cases, it's a manifold that has no codimension 1, but the same works as well. So the Grassman manifold is can be seen as a manifold embedded in the space of the symmetric matrices n by n, and it is also a homogeneous symmetric space under this action of the special orthogonal Lie group. Here we have chosen this point P0, and the isotropy group at that point is given by this, which is isomorphic to this product of special orthogonal Lie groups. And then the composition of the Lie algebra associated to the Lie group SON is given by this direct sum, where H is the Lie algebra of the isotropic group, and P is this skew-symmetric matrix, where V is a rectangular matrix. The kinematic equations also appeared in the literature. They are given by these two first-order matrix differential equations, where this psi of t is also a rectangular matrix, k by n minus k. So in this case, the derivative of this operator is also an element of P. So the idea is that we could prove for all the examples that that this holds always, but we could not prove theoretically that In fact, this is an element of P when the ambient manifold M tilde is non-Euclidean. So that's what we are trying to do at the moment, but it seems that it's not easy. So thank you for your attention.